Yeah. Hi, everybody. Welcome to the first edition of the Fall 2021 PAW seminar. Our first speaker will be Jaume de Dios, who will speak on uniform boundedness for certain operators parameterized by polynomial curves.
So, hi, everyone, and thank you to the organizers for inviting me and let me speak about uniform boundedness for operators parameterized by polynomial curves. So I'm going to start by introducing some examples of operators that depend on polynomial curves, and like we will see what the main idea is more like through examples than anything else. So the three examples that we're going to look at first are convolution against a polynomial curve, restriction on a curve, or Fourier decoupling in a neighborhood curve. In the typical problems that we consider, we always start the same. Start with let gamma be a smooth curve with a non-vanishing torsion. As a reminder, what that means is that the determinant of gamma of t, gamma prime of t, gamma prime of t, all the way until gamma to the d of t, which is a d by d matrix, is not equal to 0 anywhere. In dimension 2, which is the maybe most intuitive case, that means that your curve has curvature all the time. It does not like become flat at any point. So you start with a curve like that, and then you define this operator T gamma, which is some sort of a convolution, but only in the direction of gamma. So you have your function, and then you average it out. When you average out a function, you expect to get some sort of upgrade on the integrability properties of your function. You start in L1, maybe you get to L2, or you get a bit higher. And this turns out to be the case for these particular pairs of P and Q. If your function is in LP and you take these sort of averages, you upgrade it to LQ. And then you have a bounded operator where the bound a priori may or may not depend on gamma. If you look at this operator for a second, you might realize that the adjoint of this operator is very, very close to this operator. So in this particular case, the adjoint of this operator is with a plus self of a minus. That already gives me another bound for free in this case, which is a bound from LQ prime to LP prime, because having a plus, having a minus is going to be the same. So I also get another bound for free. And this operator, of course, also maps like LP to LP for any P, because it's just like averaging and smoothing out. So this is kind of like a model operator that we care about. Next thing that I want to talk about, because I referred to torsion, but you could define this operator perfectly without having to look at any kind of torsion type estimates, but they fail. So I'm going to look at the most degenerate example. So there's this curve gamma of t, which is a segment, which is like just run at uniform speed. And we're going to see that for this particular choice on gamma, we have no LP improving estimates. The counterexample, the reason why we won't be able to have LP improving estimate is going to be a tube. So this function is a characteristic function of a 3D tube, but we can just picture it in 2D. And the same example does work in 2D or in 25 dimensions. And then the function supported here. Our curve gamma is supported on a line. So when we do this kind of convolution, we will end up with a function, so this is f, and then T gamma f will be supported on a line that's going to be like twice as big, equally wide. And therefore, like the f and T gamma f are going to look essentially the same. Maybe like it's going to be longer, like the support's going to be a bit bigger, but they're pretty much the same function. If you do the computations explicitly, you can, in this case, they're easy enough that you can actually do them. But what matters is that the support is the same, and therefore, you get this estimate on the LQ norm, which is analogous to the one you get for the LP norm. By letting epsilon go to 0 or go to infinity, you see that you cannot expect any non-trivial estimates for this case of gamma. if you have a curve that's supported on a plane, like for example, let's say that we consider for a second t squared, 0, here I could still run examples that would be like chi minus 1, 1, chi minus 1, 1, chi minus epsilon, comma epsilon. So, and I could still find counterexamples. So this is the reason why we need to have enough curvature. We need to, in some sense, our curve to locally at around any point be filling all the dimensions of space to counter potential counterexamples like this. And those counterexamples are, in fact, all you need. If you can show that, like, if all characteristic functions work in this example, like the P's and Q's that you get are the ones that are totally determined by these characteristic functions. Another typical example that I wanted to talk about is Fourier restrictions, one of the central problems in harmonic analysis. But in this case, we're going to look at it on a curve. So again, we're going to start with gamma smooth curve with non-vanishing torsion. And now you define the restriction operator as the Fourier transform restricted on gamma. So you will have a function that's going to be supported somewhere. Then you will take its Fourier transform, which will be supported somewhere else, like in this case, maybe something like this. And you're not going to look at it everywhere. You're just going to look at what happens to this function, to f hat, exactly at gamma. And then when you compute the LP norm, you will compute the LP norm with respect to the arc length measure on gamma or the time parameterization measure on gamma, which is what we're going to do in this case. So we will compute. So in this case, what we're interested in is, like, if we start with a function which is in LP of the whole space, and I Fourier transform it, and I only look at this in gamma. And in this case, for example, I get a function that's only on 0, 1, because it's like f hat of gamma of s, which is in 0, 1. Which P's and Q's make this a sensible operator? And again, turns out that the answer is whatever characteristic function study. But it's actually quite better to look at the adjoint of this problem as before. So in this case, the adjoint of this problem is the extension operator, which is the same operator, but when you look at it, it can look a bit different. So you start again with a curve with non-vanishing torsion, and then you define the extension operator as an operator that gets a function and computes its Fourier transform, but only with respect to the curve gamma and not with respect to the whole space. And of course, you get, since this operator is the adjoint of the previous one, you get the dual exponents. The last example that I wanted to talk about is the coupling. The coupling might be a bit of a more modern type of operator, and I'm going to explain it with a picture before going into the math. So the idea of the coupling is that you have a curve gamma. In this case, I'm going to draw a parabola. And you imagine a collection of functions which are supported near, but maybe not exactly at your function. You can consider functions supported at your function with a measure, but it makes things more complicated. So we'll just look at functions supported near. So here I'll have my function f1. Here I'll have my function f2, f3, and so on. And this would be like a small distance delta. And this is going to be much, much smaller than delta, like delta to the d, where d is the dimension. So I'll have like those tiny tubes around my curve. And functions supported on them, or like f hat one. Actually, like you want them to be Fourier supported here. And then you want to understand how big is the sum of the f's compared to the, we all know this. So for example, this is clear. This is triangle inequality, but you want to do better. And one way to try to be more fine is, for example, this one. And this will be our decoupling estimate. So this is like just words like written for what I just said. So you look at the tiny neighborhoods of your curve gamma, and then you look at functions whose Fourier support is supported on those tiny neighborhoods. And then you want to show something like this, like that's up to some tiny losses that you can pretend they're not there in practice. This is like a log delta or like a big power of a log of delta, something like that. Up to a big power of a log of delta, you have square root cancellation. You can have here an L2 norm, a sum of the squares, instead of just brute force triangle inequality. So there's like the fact that these functions have such different Fourier supports is forcing some cancellation when I do this sum over here, and I get a much smaller norm than I would expect. So, well, this is the coupling. And now I want to talk about patterns, like what do those operators have in common? And that's going to be like the objects that we're going to care about. So we had a curve all the time. That was very important. The problems relied very strongly on the fact that the curve was not supported on a hyperplane and that it had enough curvature in it. Once the curvature got low enough, the problem totally degenerated and the results that we cared about became false. Also, the quantities in this problem are invariant under the special linear group. What I mean by this is that if you have an estimate of this kind and you compose it, you compose gamma, for example, with an element of the special linear group, so something that has determinant 1, you will get a new operator, but it will have the same operator norm because the Fourier transform behaves very well with respect to the special linear group. There's no determinant going on. And when you look at the general linear group, you might have problems, but it turns out that on the critical line, on the edge of all the possible estimates that you care about, you actually even get GLN invariance. So everything is invariant under the transformations that we could care about. I also want to note that all those problems that meet very natural generalizations, which are also related to each other. So one natural generalization could be, for example, looking at discrete analogs. Instead of looking at integrals over the reals, you do sums over Z. And for each of those problems, you get a discrete analog. In the coupling, the discrete analog is easier. In the other ones, it's a bit more unrelated. You could also change the underlying field. For example, in decoupling, it turns out to be very important, or discrete restriction, it turns out to be very important to look at p-adic analogs of these problems, and one can get much better estimates by looking here than by just looking at the real case. One could also think of complex analogs, and complex analogs are good for two things. I think complex numbers, out of those three, complex numbers are usually the least scary one. They share some properties with the p-adics in that they are not ordered. And a lot of the proofs, a lot of the classical proofs of these theorems or of things that I'm going to show later on rely very strongly on the fact that the reals are ordered, so I can integrate along a curve. There's a strong notion of integration along a curve that disappears on the p-adics and already disappears in the complex numbers, but they're a bit less scary. And they're also the easiest toy model for submaximals. I can understand complex analogs of these problems as a very innocent restricted case of two-dimensional submanifolds in Rn. So these also hints at which generalizations are there for the statements of theorems that I will present later on. And now, what is my goal with these kind of problems? So we want to find uniform statements over families of curves. We want to show that the operators that we looked at, or the bounds, the constants in the bounds that we looked at, do not really depend on the curve that we are looking at, but they're just maybe depend on the level of complexity the curve has, but we can classify the curve by complexity and not by looking at the curve. And there's a very natural family of curves that admits a very natural notion of complexity, which is polynomials. Curves such that each component on my curve is a polynomial. And in this case, the level of complexity can be the degree. One can show that if you let the degree go to infinity in all the problems that we looked at, the bounds become worse and worse and worse. And the reason why why the bounds become worse and worse and worse is because I can start having polynomials that looks like this, and effectively they start looking more and more like a line. So I need some kind of bound on complexity because I can't have things looking more and more like a line, and the degree does a good enough job. However, the degree still has a problem. Most polynomials, and actually all polynomials, if we look over the complex numbers, for example, have points where the torsion vanishes. That's because the torsion becomes a polynomial again. It's a determinant of polynomials. It's a polynomial, and it's going to have a root somewhere over the complex numbers. And we have to compensate for that. There's a price we can pay, which is putting some weight on certain parts of the curve that compensates for the fact that the torsion is going to vanish at those points. And that gives us some hope to get some kind of estimate, because as soon as the torsion vanishes, one can use the point where the torsion vanishes to build counterexamples to these problems. And that's what we're going to do. And the weight that we're going to put is called the affine arc length measure. I will start by defining it for the reals. So this definition might be a bit daunting. What I'm doing is I have a measure over the reals. I have the usual Lebesgue measure over the reals, and I am putting a weight on it that is proportional to this torsion with an a priori very mysterious exponent. There is a way which is a bit more natural to look at this, which is by looking at this measure by how it acts on continuous compactly supported functions, so understanding this measure by duality. So, and I'm missing a gamma here. So if I want to understand how this d lambda gamma acts on a certain function, I integrate against it. And this is much easier. So what I'm doing is I am running along my curve, and I'm looking at my function along my curve. And as I integrate along my curve, I put this weight, which is optimistic because it's going to vanish whenever the torsion vanishes. And the only question that remains is, why is this the most sensible exponent to put here? But this is because this arc length measure is going to have nice properties that we're going to care. It vanishes on our potential problems. If a curve is contained on a hyperplane, then it's, how you call it? Its derivatives are going to be linearly independent, like gamma prime, gamma prime prime, gamma to the d. Cannot all be, they're all going to be contained in this hyperplane. Therefore, this is going to vanish in the whole curve. And the measure that we're going to integrate again is going to be the zero measure, and we're actually going to get a trivial estimate because like the operator will become the zero. No, I actually have this written. It also vanishes when the torsion vanishes, pretty much by definition. Like at each point where the torsion vanishes, this just dies out, and that helps us. And the most important one, and the one that made us choose this weird definition, is that it does not depend on the parameterization. It's a purely geometric object. You can have the same curve, you can look at it from multiple parameterizations, but they are all going to give rise to the same measure. And the reason for this is exactly that 2 over d squared plus z that we had there that was a bit confusing. So what I have to do is I have to look at a different parameterization of gamma. So this will be my new parameterization of gamma. And this determinant might look scary at first because I have like a lot of determinants of compositions, but I will do the first one by hand. And hopefully that will explain a bit what's going on. So this is equal to gamma prime prime composed with phi times phi prime squared plus gamma prime composed with phi times phi prime prime. Those are the two terms that appear here. And as you might imagine, like as I go further and further, here I'm going to have up to d terms appearing when I compute the d derivative. But if we look carefully at this term is a scalar multiple of gamma prime composed with phi. But gamma prime composed with phi is a term that will already appear on the previous term. And by multilinearity of the determinant, I can just get rid of it. And here I'm going to get a lot of terms, but all the terms except for the one that's going to have a phi to the d will actually be linear combinations of the terms that are coming from before. And in particular, here I will get a phi prime. Here we'll get a phi prime squared. Here I'll get a phi prime to the d. And that explains the d squared plus d over 2, because it's just the sum of it. And when I try to do the chain rule, they're going to cancel out. If I integrate, I check that the measures are the same by duality, by integrating against all possible compactly supported continuous functions. I expand this determinant, and I can get out exactly the number of phi primes that I need to do the chain rule, because I'm going to get this squared plus z over 2, but then I have this power to cancel them. And this explains why this power is the right one and why this apparently weird and complicated object is the one we actually. Now, the last thing is that it is SLD covariant. If you look at those determinants, when I had the determinant of gamma, gamma prime, gamma to the d, if I multiply this by A, this is just the determinant of A times the determinant of gamma, gamma prime, gamma to the d. So I do have like a GLN component that I recover, but no like a determinant component that I recover. But SLN reacts very, very nicely with my problem. And that that's going to be also very useful in the, and even like with GLN, it's not exactly nice, like it's not exactly the same, but I just recover a multiple. So a lot of statements are going to be the same, just by multiplying by constant. Now, I might want to extend this to the complex or p-adic case. Well, there's a natural definition. The only thing is that one has to be careful. There's two ways to be careful. This is the easy way out, where you just add here an extra factor. This factor comes from the fact that if you dilate a function by a factor of 2 over the complex numbers, then the integral increases by a factor of 4, in that like integral over c f of z let's say z over 2 dz is equal to 4 integral over c f of z dz. So when I do the chain rules and so on, I need to pick up an extra factor of 2, which can also be solved by defining the absolute value on z to be the square of the usual absolute value on z. The only thing is that one has to make sure that things become covariant when defining everything careful enough, and just making sure that the measure of a ball of radius r is r to the whatever you put here. This was already used. So the idea of extending these these problems I presented to the complex numbers was originally by Back and Ham, and they already added in the first works a factor of 2 to compensate and to make the results actually work, because otherwise the theorems that one might want to prove are actually not true. With this in hand, now we can talk about what kind of statements we expect. So for example, in the case of convolution, which was finally solved in 2017, a bit before, but that's the power state, by Stovall, she showed that in the same operator that we looked at before, except now with the torsion weight, multiple things happen. First, I do not need to integrate over a compact set anymore. I can integrate over all the reals as long as I'm working with a polynomial curve. I get the critical line. If you remember before, I also had LP to LP estimates. Those get lost now. When we upgrade to the full integral over R case, we lose all the estimates which are not on the critical line. And the most important part is that the bounds that we get do not depend on the curve. They depend on P. Of course, they go to infinity as P gets to the endpoint. No, for convolution, sorry, for convolution, they do not go to infinity. They're uniformly bounded. Actually, for convolution, this dependency on P is not there, but they depend on N, on the dimension, and they depend on the. Okay, so given this, I want to put a bit of the current situation on where those problems stand. So the real case was originally studied by Stovall, both in the restriction and convolution case, but the coupling was a very new thing at that point. So it's still being worked out. The two-dimensional case was proven by Tonggo Yang last year, and I have proven this year the general case for general polynomial curves. And then the complex case, there has been a lot of work, but the most recent situations were my proof in 2020, and then Conor Mead has been working in the complex case as well. And we are currently working together in extending the decoupling results to the complex and p-adic case, where there is a result of Woolley that proves something that is very close, but I do not think it gets all the way there. I do not think you can get all the way up to uniformity out of those results, but you definitely get it for any curve that's more than what you get in usual real decoupling. So yeah, now the rest of the talk is going to be trying to explain how does one prove those uniformity results. So the main idea on the strategy is to find a way to decompose a polynomial curve, which might be a priori a very messy object, into, and they make it messy, but not so much, into reasonable objects. Like for example, I could look at this curve and say, I'm going to break it here, 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 and I don't know, here, and say, these pieces are nice. They're like, they look convex. Maybe they have an issue at the boundary, but like each of these separate pieces, like gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, and so on, are nice enough that I can attempt to prove a theorem for them. Like for example, if your polynomial is of this form, which is always the most manageable form, then you just look, for example, at every time the derivative or the second derivative changes. That's going to be finally many times. And it's going to give you nice convex increasing or convex decreasing or one of those combinations functions. And you just cut into pieces and try to prove then harmonic analysis results for those pieces. But the most important part is that the number of pieces has to be finite and uniformly bounded. Because what you want to do is you want to say that the operator T gamma in norm is smaller than the sum of the norms of the operator of each of those pieces. And that just comes from the triangle inequality because T gamma is equal to the sum of T gamma. And I don't even know how to write anymore. So once you have a decomposition theorem for the polynomials, it usually upgrades for free to the decomposition theorem for the operator. Then you want to have some sort of GLN invariance for the operator. And that might not be as clear why now, but it becomes more clear when we see what the statements of the theorems usually are. The whole deal is that at the end, we want to be able to pretend our curves gamma 1, gamma n that we split into, we want them to be very nice. We want, for example, to pretend that gamma 1 is equal to t squared, t to the 10, or something like that. We want to pretend that curves are nice. And the way to do that will be to put our curves in certain canonical ways that will show us that the curves are nice. And in order to move them around, we want GLN or even full affine invariance of our operator. And then the real harmonic analysis comes in proving a local result for each of those curves that we obtained here, or even for tiny pieces of those curves. So basically, you usually will actually just prove a result for a tiny piece of the curve, and then use Littlewood-Paley to extend this result to the whole gamma 1 curve or whatever nice piece where like the niceness will allow you to do Littlewood-Paley or whatever analog of that you're using. And that will allow you to go from like little pieces of your curve to big chunks and like to the whole gamma 1, gamma 2, gamma 3, and then you just do triangle inequality and you're done. So that's the main strategy that you always have in mind, and that reduces usually the whole analysis to, once the base case for the moment curve is understood, the strategy reduces the whole analysis to finding a suitable decomposition theorem that will allow you to break it up nicely. And I'm going to present the first decomposition theorem, which again, for me was a bit surprising at the beginning that this was what we needed. So I'll spend a bit of time motivating. So we're working as always with polynomials. And what we're going to do is we're going to split the whole polynomial, or like the time parameterization, the real lines, into a bunch of pieces with this following property. Let's analyze this formula for a second. This over here is the determinant that we have been trying to control, the one that's inside the torsion. This is the one we cared about all the time. This over here is trying to tell us that the directions of the curve at different points are quite transversal. So I have my curve, and like the curve here, this direction, which is gamma prime at x1, and this direction, which is gamma prime at x2, are quite different. Of course, if x1 is equal to x2, I have a problem, and this will be 0. And the right-hand side has to compensate for that in some way. This van der Monde determinant ensures that whenever xi is equal to xj, so let's remember that this van der Monde is the product when I is smaller than j of xi minus xj, and I'm just putting absolute values because I have them here anyways. So this makes sure that whenever xi and xj are equal, we get a 0. Now, why? First question is, why would something like this be reasonable? And there's probably the best way to do that is by looking at some examples. So,
Joe, may I ask you a question?
Of course.
These intervals ij, are they disjoint?
In practice, yes. If they were not, you can just shrink them more.
Okay.
Like if you happen to have not disjoint intervals, you can just make them even smaller. And the larger the integral, the harder it is for this to be true.
Okay.
So yes, in practice, I think actually like in the paper, they state that they are disjoint. It becomes annoying when you go to complex numbers and so on, and you want to have nice sets. It becomes very annoying to say that the sets are disjoint. Because you, for example, want to say that you want to cover the complex plane with balls, and then they're not going to be disjoint. So either you do that or you do a very messy decomposition. So you can assume if you want that, that they are disjoint in practice. And I think in their proof, they are actually disjoint. So the first example that one could look at are monomial curves. And in this case, we have enough tools to make the computations explicit for any N1 and D. And what we do is we look at the torsion. Remember, this was our left-hand side. And it turns out that this quotient is a Schur polynomial. And Schur polynomials are polynomials that are sums of monomials with coefficient 1. So this will be sum over certain indices, x, where this is a vector x to the I. So like product of like x1 to the I1. This belongs in a certain Young tableau. It's like a whole combinatorial thing. But the whole thing is that it is a sum of non-negative terms. And then if, for example, you just restrict yourself to positive reals or negative reals, these inequalities just become AMGM because this is a sum, but then you change it for the square root of the derivatives over cardinality of t. And then this is at most the product to the 1 over cardinality of t. And this turns out to be exactly equal to this torsion over here once you compute what this torsion is and do the computations carefully. So monomial curves, and this is a very telling example because, and if I have to do a bit of spoilers, it turns out that, that as we're going to see in the end, if you have any polynomial curve, you can break it into pieces that up to an affine transformation look like this. So those monomial curves are in fact as general as it gets, up to breaking into pieces, which Dendrinos writes allows us to do. Then another particularly easy case is the two-dimensional graphs of polynomials case, which might be the first case where you have some sort of complexity. These guys are scale invariant. So in fact, you have it at a point, you have it everywhere. And in this case, you can just compute that determinant of, we compute this. So it's like 1 p prime of t1. So this is gamma prime of 1, gamma prime of t1, and then 1 p prime of t2. This is exactly equal to this, divided by t1 minus t2. And I am using t's instead of x's, but the idea is there. And now you just have to prove this. And in this case, you can again do AMGM. You can just throw this in the middle. And this works just by partitioning p and p prime to have constant sign. So like you'll have like pieces going up, pieces going down, but everything's going to be like either convex or nice. So like you partition like into pieces like this, and then like this, and then like this, and then like this, and so on. Oh wait, and I have to partition here as well. So there's like a very nice algorithm to just partition in these particularly easy cases. And then the last example, which also is quite telling that something like this could be reasonable, is affine transformations. If the Dendrinos right holds for a curve gamma, then it also holds for A gamma. That's because if you look at the inequality, you have all those determinants. And if you put A's here, you can pull them off by multiplicativity of the determinant, and they cancel out on both cases. So this one is not just like SLN invariant. This inequality is like purely GLN invariant. And turns out that this inequality is enough in the real case to show uniform boundedness for convolution and restriction. I do not know how to use this inequality only to prove the coupling, but I know how to do it using another decomposition theorem that I will present now, which also works over the reals and over the PRs. But before that, yeah, let's talk about why. Those inequalities are a bit, I mean, they're super useful, but the first time you look at them, at least the first time I looked at them, I was a bit taken aback on why was this so central into those results. And there's a short story which we'll look into a bit more carefully, which is that the left-hand side, which is this, is the Jacobian of this sum map. And we're just trying to say, so the Dendrinos right is just trying to control this Jacobian and say that this Jacobian is quite big. And now why would one care about this Jacobian? And the reason is because this Jacobian also controls how certain multiple convolutions are. So we have this object, which is, I have my function convolved with lambda gamma, and I convolve it n times. And this is actually, it's not here, but this is d times, like the dimension, default convolution. I hopefully don't have to convince you that looking carefully at convolutions is going to be important for the convolution problem. But looking carefully at convolutions is also very important for the restriction problem, because we know this. We know that the extension of gamma, the extension at gamma of a function f raised to the n is the Fourier transform of f lambda gamma, not to the n, to the d that I mentioned, f lambda gamma convolved f lambda gamma, f lambda gamma. And the whole core of the proofs of proving boundedness for the restriction operator is using this together with Plancherel and a very clever induction on P argument. So like you start like with one utility argument, and you use this fact with a very clever induction on P argument, and you need to bound at each step how big these convolutions are, and in particular, you need to control how big they are with respect to the Lebesgue measure. And it turns out that if the function f is nice enough in that this sum map is one-to-one, which you can assume after breaking it into enough pieces as well, then G evaluated at the sum of certain points has all the ingredients that you would imagine. So a product of the contributions coming from each point. It has an f, and it has this term that comes from the lambda gamma. Lambda gamma had those geometric terms appearing. It's a product of all of them. That's reasonable because in a convolution, there's an integral of a product. There's a k factorial. The k factorial is also reasonable because there's a contribution coming for each possible permutation of the T1s. And that gives the k factorial. And the only extraneous term is this determinant, which is the determinant that the Dendrinos right is trying to control. This determinant comes from a change of variables. It's controlling like, it comes from essentially from like how you have to change from these variables to the usual variables. And you can see it by duality by choosing, by using the representation formula of the measure. You use this formula, and from this formula and careful algebra, you essentially get this. And now you want to change variables, because in the end, you do want to make not an integral with respect to the sums, but you want to have an integral with respect to the usual integral on H. And when you do this change of variables, remember that the Jacobian of this change of variables, or at least the opposite change of variables, was phi. So when I make the change of variables and I recover a Jacobian, I get the inverse of the Jacobian in this case, which is this. And that's what this shows up. So now I will provide the composition. I will just outline the composition, like how do you prove it, that extends Dendrinos right and that works over complex p-adic fields and also other fields that appear in the process that I'm not going to talk much about, but I'll have to give some definition. First one, generalized moment curve. I already talked about those curves, or you can also call them monomial curves. There are curves that have on each coordinate a monomial. They're going to be the models. They're going to be the base pieces. Our main goal is to say that each polynomial curve is actually just made by cutting and pasting pieces, up to a very small error by cutting and pasting pieces like this. And when I say up to a small error, we have to be careful because we have potentially pieces that have infinite size where the errors can become arbitrarily large. So we need to write a suitable definition of similarity. And in this case, it's this one. So I'm going to say that a polynomial is similar to a monomial in an annulus. So I'll have this is going to be little r, this is going to be big R. And then similarity is going to depend on these two parameters. So I'm going to say that I'm similar here. And there's a bunch of technical conditions, but in practice, what I want to say is that the monomial here that has the z to the n dominates all the others. So basically what this tells me is that the monomial coefficient for z to the n is almost 1. And that for any point that you pick inside here, the size of the monomial is going to be such that that term cannot win. That term is always going to be at most epsilon. When you substitute here, this term is going to be at most, any monomial that's not n is going to have size at most epsilon, the contribution of the monomial n. So essentially there's one monomial that's much, much bigger than all the other ones, and epsilon just controls how much bigger. There's also another definition that's equivalent to this one, which is as follows. If you're in an algebraically closed field, which by working hard you can always assume, you're epsilon similar if and only if for another much smaller, where that has to be made precise, annuli, all the zeros of P are either out here or in here. So you have a protection area where you're guaranteed that you're not going to have any zeros. And that's another definition of similarity, which is equivalent for algebraically closed fields. And sometimes it's much more useful because it lets you gain similarity by just knowing where the zeros are. And then similarity for polynomial curves is going to be the same. So I'm going to say that a polynomial curve is similar to a generalized moment curve if each coordinate is similar to a coordinate monomial curve. So there is no mystery here. And with that in mind, we can state the composition of the curve. So we start with a local field of characteristic 0. If you want, you can think K is equal to R, C, or QP. It turns out that you need to add a bit more things for the proof to work. You cannot stop here. If you stop here, the proof doesn't work. You need to add a bunch of field extensions of QP if you want things to run smoothly. And you start with a degree n polynomial curve. Then one can split K into open sets. And now here the disjoint property becomes tedious. So in this case, it's probably better to not assume disjointness, such that for each, okay, let's try to unpack this. What this is telling me is that for each of those pieces, so I'll have a piece here, that's going to come from this decomposition. I'm drawing it ugly. In fact, they're nice. They're like triangles, but I'm just drawing it as something, whatever. I can fit it inside an annulus. And in this annulus, my curve is essentially a moment curve. So I'm going to have, in fact, like this area is going to be split. This annulus is going to be split into a bunch of pieces. And each of them is going to be an ij, I1, I2, I3, and all of them, like by using a bunch of those annuli, I'll cover the whole space. But not only that, in each of those ij's, not only I'm very similar to a moment curve, but the conclusion of Dendrinos right holds us. And in fact, what happens is this. Like I show that I'm so similar to a moment curve that I can translate Dendrinos right into my curve. How do we go to prove something like that? So the K tools are as follows. First, we don't look at a single curve. We look at all the possible curves at the same time. At least we don't look at the ones that are contained in a hyperplane because those ones we already decided that they were very degenerate. So we assume that our curve is not contained in hyperplane. And then we're gonna, in this space, we're gonna look at various objects. The first one, which is interesting, is that this determinant that came up in the inequalities that we looked at is a continuous function on gamma. So like the map that sends gamma to this polynomial. Oh, my pen has stopped working. The map that sends gamma to this polynomial is a continuous map from the space of polynomial curves to the space of polynomials. And not only that, I can understand this object at the diagonal as Z1 and ZD are equal. I could come up with a 0/0 situation, but you can actually overcome this situation. And you can show that in the worst case scenario, when Z1 and ZD are all equal, you recover the torsion. So that this object that showed us how far away, how dispersed were the different derivatives from each other, in fact converges to the torsion as the points go to 0. The next tool that we need is some sort of compactness. It turns out that this space, if you look at it up to affine translations, it behaves like a compact set. And I must say, this is my least favorite part of the proof. There has to be a very nice compactification of this space that makes the proofs true just by compactness and don't have it to look at it. In practice, I do not know how to do that. And I have to do a lot of passing to subsequences all the time. I will not do that here. I will pretend this space is compact, and then we'll be like much faster and save like multiple pages. And then positivity, I already commented this before. This is positive. Like all the monomials in this polynomial are not negative. This is going to be very important because from here, as you saw, we derived for free that the Dendrinos right inequality was held for generalized moment curves just by knowing this positivity. This positivity is all the input we're going to need to show Dendrinos right. Now comes the key idea. The key idea is that the torsion, this determinant, gives us so much information about the curve. In fact, if we know that a curve, that the torsion on a certain annulus, so we have a big annulus, which is this one, and we know that in this annulus, our torsion is very similar to a monomial. Then on a slightly smaller annulus, our curve up to an affine transformation is very similar to a monomial curve. So we can upgrade from understanding very well the torsion to understanding very well the whole curve. By compactness, it turns out that you can derive this argument, this result, from this is a uniform result, and you can derive it from a cheap pointwise result. The cheap pointwise result is as follows. If if the torsion as before now is exactly a monomial, then the curve itself has to be a generalized one. So we can go up just by proving a pointwise result. Using compactness, we can go up to a uniform result. Something that I want to comment on is that this is very false if you're in the smooth category or C infinity. This works for polynomial because of a dimension counting argument. Like the dimension of this space is much bigger than the dimension of where the curve lives itself. So there's enough room for something like this to be true. But as you go to infinite dimensions, all these dimension counting arguments, like, okay, no, this is a dimension heuristic, not an argument, it's like a proper argument. But those heuristics totally break, and you can actually build counterexamples where the torsion is would make you think you have a moment curve, but your curve actually oscillates terrible. It's a very specific statement about polynomials that does not generalize. Okay, so but the point now is that we only have to decompose the torsion. If we find a decomposition that works for the torsion, we will be able to upgrade to a decomposition that works for the whole polynomial. How do we decompose the torsion? Well, we just need a result like this that tells us that we can split our field into annuli where the torsion behaves. Wait, if I put this, I don't need any of this, I just need X, where the torsion behaves like a monomial on each of those annuli. And to do that, we can use the geometric interpretation of similarity. Essentially, if we assume that P splits into linear factors in K, which is why we needed to actually add a lot more fields so we could do field extensions and all that algebra stuff, then you just look at the locations of your zeros, and you can show that you can use those locations to build annuli that protect your zeros. And then here I would have to build smaller annuli, maybe I'd have to put some annuli with like inner radius equal to 0 here. But the number of annuli that you're going to need, and then there's like one annuli at infinity, the number of annuli you're going to need is only going to depend on the number of zeros, which is equal to the. So that's how you prove that. And it's like a purely combinatorial result because you're back in one dimension. We understand what happens in one dimension. And it's okay. So as just wanted to bring back the whole main strategy that we had. I just revisit it now that we understand how the theorems works. So we have a decomposition theorem for polynomial curves. You can either use Dendrino's right, or you can use this extended version, which is going to give you the composition theorem for your operator. And then once you have GLN invariance for your operator, you can go to only look at local results. Now you can pretend that your curve is mu equal to z to the d1, z to the d2, z to the dd, and you can see that I'm not great at choosing letters. And then it turns out that you can further split this curve into pieces that look like a normal moment curve. And then on top of that, do little Paley to recover from this curve, this curve. And then just, you know that every curve looks like this in any place, so you're done. Now, to finish, what's there to be done? As you saw in the table before, the convolution estimates are still to be done. So it's probably what I would like to focus on later. You can try a lot of other operators. And that's something that I would like to ask everyone about. Like, do you have any operator in your life that you would like to make uniform? And then this is a big scary problem involving a lot of algebraic geometry. How can we extend these decomposition theorems to higher dimensions? And also in the discrete setting. There are proofs of uniformity in the discrete setting, but they very often rely on very different techniques. So can we find the decomposition theorem in the discrete setting that lets us prove theorems? So yeah, that's it. Thank you very much.
Thank you so much. Questions, please.
Hi, Joe, may I have a question?
Hey,
I'm trying to understand why polynomial is important. Suppose you have a general curve and you know that the torsion changes sign finitely many times. Do you have counterexamples in that class when this operator from LP to Q is not bounded for P and Q?
Not off the top of my head, but I know that I can build arbitrarily terrible curves with torsion equal to 1. So I would have to look at those counterexamples, but there might be counterexamples even when the torsion changes finitely many times. I'm thinking like on some sort of like spiral that does like this.
Close to hyper.
And then, yeah, it becomes too close to something. I would have to look at it, but it doesn't look impossible that things become very messy. It's not only cluster hyperplane, but as soon as your, how you call it, as your curve intersects a line in infinitely many points, you can already use that to build a counterexample. Very often, maybe not always, but like in a lot of situations when you have something like this, you can exploit this line to put a lot of mass in this line and try to gain, or to lose integrability. But I cannot provide an example off the top of my head now. So yeah.
Okay, so sign change doesn't matter, right?
I don't know, but I wouldn't think so. Like I think if there's something, and polynomials are like, the proofs, to begin with, like all the techniques that I use totally break as soon as you don't have polynomials. The key idea that I use just gone. There's no analog, like there's nothing even reasonable to substitute it. But I also think that one might be able to build counterexamples. I don't know about how, if like you add like extra conditions like analyticity and so on, but like for relatively nice, for relatively non-nice curves, definitely, I think you should be able to build counterexamples.
Okay, thank you. Thank you for the great talk.
Are there any other questions? Okay, well then, please let's thank our speaker again for a great first talk to enter PAW into the fall semester, and I wish everybody to have a great fall semester.